So let's go to the next presentation, also from RMIT. I'd like to invite Dr. Mojtaba to start your presentation.
Yes, good morning, everyone. Just let me share the presentation. Can you see my slide?
Yes, thank you.
Okay, yes, this work has been done, is an ongoing project, I can say, at RMIT University, and we're trying to develop an intelligent maintenance system for maintenance of port infrastructure, which is called Digital Twin. So together with our industry partner from BIA company. So let's try to move to the next slide. Okay. Australia relies on sea transport for more than 98% of exports every day. $1.2 billion of trade moves through Australian ports, which is and also a substantial proportion of our domestic freight depends on coastal shipping. And so these are very critical infrastructure for Australia. So if a structural element or a structure within a port fails, the resulting problem often is not just the cost of repair, but also the social and economic cost due to forced closure. A closed port may mean thousands of dollars lost every hour. And therefore, monitoring of structural assets within ports is of great importance. The focus of our study, or our case study, actually is one of the ports in Queensland, which is Dalrymple Bay Coal Terminal, operating since 1983, and it's one of the major ports for exporting coal from Australia to overseas, with a live capacity of 2.28 million tons, including 3.8 kilometers of jetties, which convey the coal from stockyard to the RAF. And obviously, exposure to the marine environment make the aging and degradation of these assets much faster. Our focus in this study was on the superstructure, the steel truss, which actually the belts are moving over them, those conveyors, and we work on modeling of L15 conveyor, which is located here, but more than around 150 of these conveyors exist. So a critical structure for the asset owner at Dalrymple Bay Coal Terminal, which actually the current maintenance is through mainly visual inspections, which is done regularly. But what we are aiming is to develop a digital technology solution for this infrastructure in collaboration with our industry partner. So a digital twin is an up-to-date digital representation of a real asset in operation. This concept of digital twin has been used in manufacturing sector for ages, I can say, and they're gradually being adopted into the civil infrastructure sector. However, more fundamental research to advance and integrate multiple technology to create digital twin is required. So this is a movement towards digital driven asset management system. What we mean by digital twin is that actually we have our physical infrastructure equipped with some wireless sensors, which send the monitoring data remotely to our data logger, and the asset engineer in his office look at the digital model of the infrastructure and can observe in real time how the structure perform against the loads or environmental condition. So it's a real-time digital model of the physical infrastructure. This digital twin is actually is a integration of 4 technology, I can say. So we have Internet of Things, where we have wireless sensors installed on the physical infrastructure and using cloud and under cybersecurity systems, the data remotely is transferred to the data logger, and we need to make a finite element model of the structure of interest, which can in real time give us the output of structural integrity, how stress are distributed, or about the deflection of the structure, or any defect of the structure can be observed in real time. So I think everyone knows that how computationally expensive is the running of finite element models. Therefore, for having real-time finite element model, we need to use some techniques such as reduced order modeling to actually make the FEM model more time efficient. Also, what we propose is to use of virtual sensor techniques in addition to those physical wireless sensors, to actually have more cost-effective sensor system. So these virtual sensors actually help us to have less number of sensors in total. Then another part of this digital twin is advancing artificial intelligence technique, because we want our system be intelligent. Therefore, we want the digital model tells us, for example, tell the asset owner which structural element needs repair or replacement first. So a prioritization algorithm should be there. So for that, we can use fuzzy set theory and MCDM methods, which we have already developed, but it needs more development and integration into the system. Also, to equip our intelligent maintenance system with what if scenarios. For example, the asset owner wants to know how repair or strengthening of one element or one part of the structure can affect the overall structural integrity. Then we can use some machine learning technique to advance what if scenarios and have our digital model equipped with this technique, which actually make the model intelligent. Then the last part of the digital twin is where we actually visualize the output of the model. So 3D visualization is the other technique that need to be developed for having an intelligent maintenance system. So how do we deal with big data and data analytics and image processing is another challenge that we have in this project. So what we propose is using already available beam visualization techniques and integrate them to the system to create a digital twin. So as I said, those 4 major technologies exist: Internet of Things, structural modeling, finite element modeling, and asset maintenance algorithms or visualization. However, the main challenge is integration of these techniques, which requires hard work. So we actually try to work in different layers, physical layer and cyber layer. We have our sensor and data gateway in our physical layer. Then we need to have a connection to our cyber layer, which is the data processing part and 3D visualization. And then where we have human interaction, we need to make sure our decision support system, which is integrated to the system, can have a good interaction with the end user. The work which has been done so far, actually we determine where we need to put the sensors on the steel truss. This is L15 conveyor, and we did initial finite element modeling to see where we have maximum structural reflection to the loads, for example, where we have maximum tilt or maximum stresses or maximum vibration. Then based on that, we selected 3 types of sensors: strain gauge, tilt meter, and vibrometer. And in collaboration with our industry partner, we installed the sensors on the structure. So these are some photos where we put the strain gauge, tilt meter here, and then vibrometer here. And we are actually receiving remotely data from Queensland, from the sensors installed on the structure. And so we are in the process of eliminating some data. You can see some gaps here to make sure which data we are receiving from sensors need to be used for as an input to our FEM model. These are tilt for one of the tilt meter, and these are data received from our accelerometer. And parallel to that, we are actually developing the finite element model using ANSYS Twin Builder as one of the commercially available software from our software provider, Leap Australia. And we are dealing with the challenges of communication of input data from sensors to the FEM model in one hand, and using reduced order modeling to actually reduce the time for running that finite element model on the other hand. So this is the work which is in progress. And again, I need to emphasize that the integration of these technologies is the main challenge that we are dealing with, and we hope we can progress well on this. So benefit of digital twins, I think everyone might know that digitalizing this maintenance process and moving from visual inspection towards remote sensing, and then having an intelligent maintenance system have huge benefits, which are listed here, and so risk will definitely be reduced. We can do preventive actions before any failure happens, and prevent closure or shutdown of such critical infrastructure which need to work 24/7, and every hour of shutdown is very costly. And some figures which are from literature, and we think moving towards the development of digital twin can help the economy and asset maintenance, are listed here. These are from literature. For example, digital inspection and maintenance can reduce the capital investment by 3 to 5% by extending the useful life of infrastructure. Or on average, using a digital twin saves asset owners between 20 to 30% of maintenance and development costs, and considering billions of dollars spent annually for maintenance of infrastructure, shows how huge the contribution of development of digital twin can be for infrastructure maintenance. Thank you.
Thank you, Mojtaba. That's excellent presentation, and it looks like a really big project. So well done to you and the team. So any question for Mojtaba?
Yes, can I ask a question?
Please, yes.
Hi, hello, this is James Gong from Deakin University. I enjoyed your presentation. That's a very good topic, digital twins for the port infrastructure. I guess my question is around the cost effectiveness, and how do you put up this so-called business case? As we know, this is all very good concept in digital twins for infrastructure, and doesn't matter it's in bridge or building or port or water. But my understanding is it is quite expensive at the moment. Requires lots of capital investment and also ongoing operational cost. So lots of money involved. And when we talk to the industry, the biggest challenge is they said, well, what's the benefits? How can we put up a business case? They simply cannot find enough justifications for such a big spending. So any comments on that? Thank you.
Yeah, I think digital twin is a well used concept in some other engineering fields, such as manufacturing or aerospace engineering. So in those sectors, they found it's very beneficial and cost effective, and they are using it. Yes, for civil infrastructure, as you said, it needs capital investment. You need to buy sensors, you need to install, you need softwares to operate, to actually integrate. And but if we consider whole life cycle of the project, like 40, 50, or 100 years of maintenance, which you eliminate the cost of inspection, visual inspection by inspectors, risk of inspection, and also on the other hand, you improve the accuracy of monitoring. So in overall, considering whole life cycle cost, then I think digital twin can suggest less cost. But yes, it needs a good study. I can say, based on the comment I received from civil infrastructure asset owners, I think they see the benefit of this, and they are moving towards that. Our industry partner, for example, in Darling-Pelbeek coal terminal, started to actually collaborate with us and install the sensors there, and to proceed with this project. Also, I received from other industries or asset owners some good feedback and some motivation to move towards this digital twin concept. So yes, it's very new for civil infrastructure, but I see good motivation from industry.
Yep. I think that's really good question and also very good answer from you, Mojtaba. So I think because of the time, let's move on. And I'm sure if you have questions, you can reach out to Mojtaba on the chat box. So